Hello, sir. You can start,
Hi.
sir.
Good evening, everyone. Good evening, all.
Good evening, sir.
We learned last class relative lowering of vapor pressure. Continuation of that we'll have to learn. Right. So I'm just looking out the space to write something. Right. I'll write here. Don't worry about this question. We need space to learn. All right. So now when we started the chapter and we said we understood otherwise, dilute solutions behaves like a gas. Dilute solution behaves like gas. We learned it. Why dilute solution behaves like gas also, I told and explained it to you very well. Now, when we talk about a gas, how many types of gases you know? How many types of gases you know? How many types of gases you have learned? Have you learned ideal gases and real gases?
Yes, sir.
Yes. Now, ideal gases and real gases. What is ideal gas? A gas which obeys Boyle's law and Charles' law. At all conditions will be called as ideal gas. And real gases will not obey Boyle's law and Charles' law at all conditions. That's called as real gas. But in nature, there is nothing called as what? An ideal gas. There is no ideal gas. All the gases are real. But these real gas can be made to behave like an ideal gas. That's a different part of the topic. Anyways, we are not talking about the gases now. Since dilute solution behaves like gas, I had to start with this. Now, this dilute solution are also classified into two. One is called as an ideal solution, and the other will be called as non-ideal solution. The other one will be called as non-ideal solution. Now, what is this ideal solution and non-ideal solution? You'll have to understand the ideal solution and non-ideal solution. Now, we have learned something called as Raoult's law. Can anyone define what is Raoult's law? What is Raoult's law? What is Raoult's law? What is Raoult's law? We learned it. Partial pressure of a component will be equal to what? The vapor pressure of a pure component into, excuse me, into the mole fraction. We have learned this formula. We have worked out problems also based on this last class. All right. Partial pressure of a component will be equal to the product of partial pressure of a pure component into the mole fraction of the pure component A. That's called as what? Raoult's law. Or we also learned Raoult's law to be the relative lowering of vapor pressure is equal to the mole fraction of the solute. We have learned all this. See here, Raoult's law limitations also we have learned. See, Raoult's law, we have learned that as what? The vapor pressure of a solution is the sum of the partial pressure of the components. That is the solution of two volatile liquids. We have learned it. So Raoult's law we have learned. The other alternative way of defining relative lowering of vapor pressure is equal to the mole fraction of the non-volatile solute. We have learned this. And we have learned Oswald-Walker's method also. I just referred to you what is Oswald-Walker's method. We'll have to work out the formula for that I told you. So this is the formula to calculate. This is Raoult's law. This is the mathematical representation of Raoult's law. Now, What is this ideal solution and non-ideal solution? A solution which obeys Raoult's law at all conditions. A solution which obeys what law? Raoult's law at all conditions will be called as ideal solution. A solution which does not obey Raoult's law at all conditions is called as non-ideal solution. Did you understand this? First difference? What's the first difference? Ideal solution, a solution which obeys Raoult's law at all conditions is called as what? An ideal solution. A non-ideal solution, a solution which does not obey Raoult's law at all conditions will be called as what? Non-ideal solution. Did you follow this 2 point? First point. Did you observe? Did you understand this first point?
Yes, sir.
Now, the second point is, now you have to answer me this question. Now, if I take heptane and I take hexane, normal hexane, normal heptane. I take 100 ml of this and I take 100 ml of this. When I take 100 ml of both, what happens when I mix? When I mix, I get a mixture, and that mixture, what I get, what will be the volume of that mixture? What will be the volume of that mixture? How much it will be? 10 plus 100 plus 100. What will be the volume of the mixture?
200 ml.
Now, what will be the change in volume? When I say change in volume, the mixture volume is 200, and the material what we have taken to prepare a mixture, that is again 100 plus 100. Therefore, delta V, that is change in volume of mixing, is what? 0. This is the first point. We'll try to understand. This is the first point. Second point is, now this heptane and hexane do not react with each other. When they do not react with each other, it neither absorbs energy nor it what? Gives out energy. Neither it's endothermic or it is exothermic, since it does not react with each other. Therefore, delta H of mixing is also 0. What is delta H? It is enthalpy, heat. When we mix two solutions, there is no change in enthalpy because there is no reaction between these two. Those kinds of solutions are called as what solutions? Ideal solution. In case of ideal solution, when you mix two solutions, there should not be any change in what? Volume. If you take 100 ml of hexane and 100 ml of heptane, when you mix these two, you will get 200 ml. Therefore, it is called as an ideal solution. Likewise, the third point is, when we mix two solutions, there is no heat liberated nor heat absorbed. That is why we say no reaction is there between heptane and hexane. Therefore, the volume of mixing is exactly what? 200. 100 plus 100 exactly gives you what? 200. We will take examples and see later. We'll see later. Now, examples, I just gave one example. Few more examples we will learn. One is what we learned, normal heptane and normal hexane. You should remember few examples. All right. The second example is chlorobenzene and bromobenzene. These will not react with each other. So therefore, the volume remains the same. If you take 100 ml of chlorobenzene and 100 ml of bromobenzene, when we mix both, the total volume will be 200. Therefore, delta V of mixing will be 0. Since they do not react with each other, delta H of mixing also will be what? 0. The next example is benzene and toluene. This benzene and toluene is also an example for an ideal solution because they do not mix with each other. All right, therefore, delta V of mixing will be 0 and delta H of mixing will also be 0. Now we will take an example and then we'll understand. I'll erase this. Can anyone tell me what is hydrogen bonding? What is hydrogen bonding? What do you mean by hydrogen bonding? Anybody? What is hydrogen bonding?
Sir,
What
sir,
is
they're weak bonds, sir, of hydrogen which connect the molecules, sir.
Of what molecule? What ion it will react with? What element it will react with? It's a force of electrostatic force of attraction between hydrogen atom and highly
Yes,
electronegative atom. It's
Yes,
called
sir.
as what? Hydrogen bonding. Highly electronegative atom like fluorine, oxygen, nitrogen, those will be called as hydrogen bonding. Now, coming to this ethanol. Ethanol is an alcohol which is, used for preparing the consumable alcohols. Okay, that's ethanol. No other alcohol can be consumed. Only ethanol can be consumed. Now, what I do is I take 100 ml of ethanol, and to this we take 100 ml of water. When we add 100 ml of ethanol and 100 ml of water, we get a mixture, ethanol water mixture. Now, the ethanol water mixture will be around 210. It will be around what, 210. Why it is 210, we will learn that little later. Now, the next example, this is the first example. The second example, we take HCl, 100 ml of HCl, and to this we add 100 ml of water. When we add 100 ml of water, the expected volume is 200. The volume what we observe for a mixture will be 198 ml. What's the volume of the mixture observed? It's 198 ml. Why? We will learn. Now, in case of ethanol, this ethanol is C2H5OH. And water, we write it like this, a pent molecule. What happens is there is a hydrogen bonding formed between oxygen and hydrogen. Oxygen of water molecule and hydrogen of ethanol molecule. So this hydrogen bonding is a longer bond. What happens? Volume increases. Volume increases. That is why delta H of mixing, delta V of mixing should be equal to 200, but it is not equal to 200. Why it is not equal to 200? Because of the formation of hydrogen bonds. Since the hydrogen bonds are longer, what happens is the volume increases. So therefore, you get 210 ml. That means in case of non-ideal solutions which does not obey Raoult's law, the second difference will be what? Delta V of mixing is not equal to 0. Why not equal to 0? Because of the chemical reaction. See, there's a reaction here. Ethanol reacts with water to form a hydrogen bonding. Therefore, volume increases. The second example, if you observe very carefully, this is HCl and water. When HCl is added into water, it's an exothermic reaction. When I say exothermic reaction, delta H is negative. Exothermic reaction, heat is liberated, heat is given out. When heat is given out, what happens? Some amount of water can vaporize. Some amount of HCl also can vaporize. Since this some amount of HCl and water vaporizes, what happens is the volume decreases from 200 to 198. That means even in this case, delta V of mixing is not equal to 0. Expected volume is what? 200, but observed volume is what? 198. It indicates delta V of mixing. When you mix an acid with water, there is a reduction in the volume. Why there's a reduction in the volume? It is because of the reaction, which is exothermic. An enormous amount of heat will be liberated. Therefore, what happens? There will be loss of there will be loss of some of the water molecules that HCl. Therefore, there decrease in volume. Likewise, the third observation is delta H of mixing. Delta H of mixing is also not equal to 0. Just observe here. In this case, HCl and water, we learn delta H of mixing is negative. Why delta H of mixing is negative? Because it gives out what? Energy. There is energy liberated. But likewise, delta H of, for certain solutions, delta H will be equal to positive also. That is why in general, we have learned delta H of mixing is not equal to 0. So when we mix two solutions, when there is a change in the enthalpy, then there will that will be called as a non-ideal solution. Example for non-ideal solution: any acid and water, HCl, H2SO4. Likewise, any base and water. So all these will be example for a non-ideal solution, because in case of acid and base, when you add to water, it gives out energy. Therefore, it is an example for a non-ideal solution. And one more point we have to discuss. I think I will write it here in a different color so that you can understand that. In case of the non-ideal solution, the fourth point I'm writing here, in case of the ideal solution, the partial pressure of a component will be equal to P naught of A into XA. That means it obeys what law? Raoult's law. This is Raoult's law. Partial pressure of a component will be equal to partial pressure of pure component into what? Mole fraction of the component. Likewise, partial pressure of the second component will be equal to partial pressure of the component B pure into mole fraction of B. We have learned what is mole fraction, all that. That is the fourth difference. The fourth difference here is we can write partial pressure of A component will not be equal to P naught of A into mole fraction of A. That means it does not obeying what law? Raoult's law. So therefore, these kind of solutions will be called as non-ideal solution. Is it clear? Did you understand what is ideal solution, non-ideal solution? Difference. This is an important question to answer in your regular 11th, 12th. And still, we need to work a lot of problems on this. We will work a lot of problems a little later, completing the topic. Did you understand this so far? So any dilute solution will be classified into two. One is ideal solution, the other one is non-ideal solution. And the difference we have learned between ideal and non-ideal solution. Now, I was telling you, in case of ethanol, there is an increase in volume, and in case of HCl and water, there's a decrease in volume. That means delta V can increase or delta V can decrease. Likewise, when I was talking about delta H, I told you exothermic reaction, and I also was mentioning something called as endothermic reaction. So when delta H of mixing is not equal to 0, then we call that as non-ideal solution. We learned. Now what we are supposed to learn is this non-ideal solution is of two types. Non-ideal solution is of how many types? Two types. We will learn non-ideal solution, which is of two types. Now I'll erase this, and then we will learn non-ideal solution, which is of two types. Now, is there any doubt with this ideal and non-ideal solution, students? You can ask me. If not, we'll continue. Just give me a second. I'll erase this and then we will learn. I have to teach you 3 graphs. I will teach you the 3 graphs. Once we understand the theory part of it, then we will learn the 3 graphs regarding ideal solution, non-ideal solution, all that. All right. Now coming to non-ideal solution, this non-ideal solution is of two types. One will be as a non-ideal solution showing positive deviation. Non-ideal solution showing positive deviation. And the second one is a non-ideal solution showing negative deviation. So how many types of non-ideal solutions we have? We have 2 types of non-ideal solution. In case of 2 types of non-ideal solution, one will be a non-ideal solution showing positive deviation. The other one will be a non-ideal solution showing negative deviation. We should know the examples for this. Now, before we understand the example, we will learn the difference. The first difference is delta V of mixing will be greater than 0. Delta V of mixing will be greater than 0, or delta V of mixing will be equal to positive. When we say positive, it means what? It is greater than 0. So whenever the volume increases when you mix 2 solutions, then the solution is a non-ideal solution showing positive deviation. Example here, we learned ethanol and water. 100 plus 100, expected volume is 200, but what is the observed volume? The observed volume is 210. That means there is an increase in volume. Whenever there's an increase in volume, we call that as the non-ideal solution having what deviation? Positive deviation. Therefore, delta H or delta V of mixing is greater than 0, or delta V of mixing is positive. What do you mean by delta V of mixing? When we mix 2 solutions, what is the change in volume? That's called as what delta V of mixing. So in case of this one, you see HCl and water, there's a decrease in volume. That means delta V of mixing will be less than 0, or delta V of mixing will be negative. When there's a decrease in volume, that means less than 0, then we call that as a non-ideal solution showing negative deviation. Did you understand the first point? The second point is delta H of mixing, enthalpy, heat. Delta H of mixing, if it is greater than 0, or delta H of mixing is equal to positive, where that's endothermic reaction. If the reaction is endothermic, then we call that as a non-ideal solution. Likewise, if we write delta H of mixing is less than 0, or if it is exothermic, then it will be called as a non-ideal solution showing negative deviation. So endothermic is positive because it absorbs energy from the surroundings, and exothermic is negative because it gives energy to the surroundings. Therefore, we call those kinds of solution as a non-ideal solution showing negative deviation. Delta H is negative. Delta H is positive. Non-ideal solution showing what deviation? Positive deviation. Did you follow this? 2 points.
Yes, sir.
And in case of the third point, partial pressure of a component will be equal to partial pressure of the same component in pure state into mole fraction of this. It will be greater than the partial pressure of the pure component into mole fraction. That is Rolle's law. Rolle's law is not followed here. That's why we say the partial pressure of a component will be greater than the partial pressure of the same component at standard temperature and what standard conditions or pure component and the mole fraction. In case of non-ideal solution showing negative deviation, PA will be less than P naught A into XA. What is this P naught A? Partial pressure of a component, pure component. This is partial pressure of a component in a solution state. And this is the partial pressure of the component in pure state. So these are the differences between a solution showing positive deviation and negative deviation, non-ideal. One more point is there. The solution in which solute and solvent interaction are stronger than solute interaction. That means solute interaction. Solute, you know what is solute interaction, and solvent interaction. Solvent interaction is greater or stronger than solute solvent interaction. So this is solute and this is solvent. If solute interaction and solvent interaction is stronger than the solute and solvent interaction, then the solution will show a non-ideal solution showing positive deviation. Here it will be the reverse. What do you mean by the reverse? Solutions in which solute interaction and solvent interaction is weaker than solute solvent interaction. Those are called as a non-ideal solution showing negative deviation. Did you follow this 4 difference? See, they'll ask you in the regular class question, give the difference between ideal and non-ideal solution, or they will ask you, give the difference between a non-ideal solution showing positive deviation and non-ideal solution showing negative deviation. You should remember. Is it clear?
Yes, sir.
Now, this is this brief explanation about ideal solution and non-ideal solution. Ideal solution obeys Raoult's law. Non-ideal solution do not obey Raoult's law. All right. In ideal solution, delta H of mixing is 0. In non-ideal solution, delta H of mixing is not equal to 0. In case of positive, delta H of mixing is greater than 0. Endothermic reaction. All that heat is absorbed. All this I explained. In the non-ideal solution showing negative deviation, delta H of mixing is less than 0. That is negative. That means heat is evolved, exothermic reaction. All this I taught you. Now, you can just go through this table. Now, examples, there are many number of examples mentioned here. Please remember a few of the examples. For ideal solution, benzene, toluene, hexane, heptane, chlorobenzene, bromobenzene, ethyl bromide, ethyl iodide, normal butyl chloride, normal butyl bromide, these are. So now examples for solution showing non-ideal solution showing positive deviation. Volume will increase here. Acetone and ethanol, volume will increase. Acetone, carbon disulfide, water, methanol, water, ethanol, carbon tetrachloride, toluene, carbon tetrachloride, chloroform. All these solutions are example for non-ideal solution showing positive deviation. Volume will increase, and what's that? Maybe we can write for this. For this, we can write delta H of mixing is equal to 0 and delta V of mixing is equal to 0. Here in this case, delta H of mixing is greater than 0 and delta V of mixing is also greater than 0 or positive. Now here these solutions, acetone, aniline, acetone, chloroform, methanol, acetic acid, water, nitric acid, chloroform, diethyl ether, water HCl, acetic acid, pyridine, chloroform, benzene, all this are a non-ideal solution showing negative deviation. Now, when we say non-ideal solution showing negative deviation, here delta H of mixing will be less than 0 and delta V of mixing is less than 0. Can you remember some of the examples? Or they can ask you in competitive exam, they can give you some examples and ask you to identify whether this combination is a ideal solution or a non-ideal solution, or ideal solution showing positive deviation or negative deviation. So you should be in a position to differentiate between the compounds. Now we'll have to learn this. These are the 3 graphs what I was mentioning. We will learn the 3 graphs little later. Now, firstly, we should understand the mole fraction concept. I've been teaching you mole fraction concept from the beginning of the classes, and we have worked more number of problems also on mole fraction. Now, what is this mole fraction? Now, mole fraction is the ratio of number of moles of a particular component divided by total number of moles. Number of moles of a particular component divided by total number of moles. When I say total number of moles, it's nothing but number of moles of solute and number of moles of solvent. So totally, it's the total number of moles of solution. So mole fraction is defined as the ratio of number of moles of a particular component divided by total number of moles. Now, in mathematical representation also, I have given you, and we have worked many number of questions based on mole fraction. Now, to remind you, I'm just giving you what is mole fraction. Mole fraction of a component, okay, solute is XB, number of moles of solute divided by number of moles of solvent into number of moles of solute. Likewise, now if we take a mole fraction of a solvent, it is number of moles of solvent divided by number of moles of solvent and number of moles of solute together. This will be the formula to calculate the mole fraction. Now here, if you observe 3 graphs we have to learn. Now, I will construct the graph and explain one. The other 2 you can easily understand. You'll easily understand what it means. Now, this is a graph. This is a graph. This is a graph. Please pay attention, and then you will understand this. This is vapor pressure. This is vapor pressure. What vapor pressure of a pure component? Maybe we can represent it as P naught A. And this is the vapor pressure of a pure component B. This is represented as what? P naught B. Both the directions we have represented the vapor pressure. This is the vapor pressure of pure component A, and this is the vapor pressure of pure component B. Now this is 0. This is 0, and this is maximum. Now what I do is, here you can see XA is 1. XB is mole fraction of the solvent is XA. Here the mole fraction of solute is XB. So mole fraction of the solvent is 1 and mole fraction of the solute is 0. Now, what happens? Mole fraction of what? The solvent, which was 1 maximum. What happens as we go across? What happens? The mole fraction of the solvent keeps on decreasing. What do you mean by that? When you add a solute to it, what happens? Mole fraction of the solvent keeps on decreasing. As you add the solute, what happens? See, solute here, it is 0. And finally, this XA becomes equal to 0 here, because solute will be exceeding. Then what happened? The mole fraction of the solute becomes what? 0 here. Initially, the solvent, the mole fraction of the solute is 0. As you add a solute, what happens? The mole fraction keeps on increasing. mole fraction keeps on increasing. Did you understand these two graphs, what I told you? So x1 is maximum here on the on the left side. As you go across to the right side, the mole fraction of x1 becomes a 0. It decreases and becomes 0. Here in xb, mole fraction of the solute is 0. As you go across, what happens? The mole fraction keeps on increasing. And here, come to this, the other end, xb becomes equal to what? 1, maximum 1. Because we know that mole fraction of solute and solvent will be always equal to 1. You should not understand where did I get this number. The ratio of mole fraction of solute and solvent will be always equal to 1. So this is nothing but the vapor pressure or the partial vapor pressure of the component. Maybe I can write it as B solute. No, this is XB. No, and here this will be what? Partial pressure of the component A. Now, what happens when you add these two solutions? When you add these two solutions, you observe when you join these vapor pressures. So what happens? The partial pressure of the component will be equal to, what is that they've written? You can see the partial pressure is equal to total pressure. Total pressure is equal to partial pressure of A plus partial pressure of B. When the total pressure is equal to partial pressure of A and partial pressure of B, then we call this as what solution? Ideal solution. Then we call this as what solution? Ideal solution. Did you understand this? This graph you understood?
Yes, sir.
Others are not participating. Are you there? Anybody? At least 1 or 2 students, you please tell me. You followed?
Yes, sir.
Yeah. Now we have to talk about a non-ideal solution. I will go a little faster in teaching you non-ideal solution. Now this graph, if you would have understood, you can see this graph, what is there here and what is there here. It looks same. This is straight line. It's a straight line. It's a straight line. Now, the same graph I will use in order to teach you non-ideal solution showing positive deviation. In order to teach you the non-ideal solution showing positive deviation, the same explanation remains here. Since when you are adding the solute, what happens? The partial pressure, this is for an ideal solution, but what happens? The vapor pressure of the solution keeps on increasing. Vapor pressure keeps on increasing. Therefore, the total pressure also what increases. So this is the ideal, non-ideal solution showing what deviation? Positive deviation. See, this blue colored line is for ideal solution. This orange colored line, what I'm drawing, as you add the solute, the partial pressure of component B keeps on increasing. That is why this curve, this is a curve, increase. See, this is for ideal solution. You can see there's an increase here. Yes or no? Yes or no? In case of non-ideal solution, what we learned, partial pressure of A is equal to or greater than what? Partial pressure of component A and what? Partial pressure of component B. We have learned it or not? When we learn the differences. So this is what shows vapor pressure is what? Increasing. Here also you can see it's increasing. Are you there?
Yes, sir.
Yeah.
Yes, sir.
Now, similarly, for a non-ideal solution, what happens? The vapor pressure has to decrease. So this green color line I draw, this green color line you can see it decreases the vapor pressure. Here also the total vapor pressure decreases. See here, they have drawn this. This broken line indicates for an ideal solution. So a solution showing non-negative deviation, the total pressure decreases compared to what the ideal solution. Likewise here also. So did you understand these two graphs? 3 graphs actually. Did you follow? Here it will be what now? PA will be less than what? P naught A plus what? P naught B. Here also it should be not. This also should be not here. Did you understand this?
Yes,
Yeah.
sir.
Which one of okay, few questions and then we'll continue with the next topic. Which one is not equal to 0 for an ideal solution? Which one is not equal to 0? Delta H of mixing is equal to 0 for ideal solution. Delta V of mixing is equal to ideal solution. Delta P is pressure observed minus pressure calculated. That is also true. But this delta S, what is this delta S? S stands for entropy. S stands for entropy. S stands for entropy. Now this delta S stands for change in entropy. Entropy is what? What do you mean by entropy? If I have positive, negative, I have positive, negative, positive, negative, positive, negative, positive, negative. Is it orderly placed or not? It is orderly placed. Positive, negative, orderly placed. Yes or no? Are you able to hear what I'm talking? Ajay? All right.
Yes, sir.
Yeah. Now this is orderly arranged. Now if I say positive, negative, like this. Okay, randomly I place like this. Randomly I place like this. So what happens? There is disorderness. The measure of disorderness is called as entropy. So here, for a perfect crystal, entropy will be equal to 0 because there is no disorderness. Just imagine you're sitting in a classroom. When you're sitting in a classroom, all the students are sitting orderly. So there is no disorderness in the classroom. As soon as the bell goes and the teacher goes out of the class, what happens? You start moving outside the class. Some people will run out of the class. Some people will stay there in the class. Some people will start walking slowly. That means what happens? There is a lot of chaos in the classroom. There's a lot of disorderness in the classroom. Likewise, in case of chemicals, if the particles are arranged in order, disorderness will be 0. When disorderness is 0, we say S is delta S change in entropy is 0. But when there is no change in, when there is a lot of disorderness, then entropy will be what? Positive, or it can be what? Negative. So for an ideal solution, delta S of mixing is not equal to 0. We never spoke about the delta S mixing. When I gave you the difference between ideal and non-ideal solution, you should remember whether an ideal solution or non-ideal solution, entropy when you mix two components will not be equal to 0. There will be disorderness. There will be randomness. This entropy is also called as measure of randomness, measure of disorderness, or measure of randomness is called as entropy. So measure of disorderness or randomness is called as entropy. For an ideal solution also, entropy will not be equal to 0. There will be a lot of disorderness. The next question, which of the following solution shows positive deviation from Raoult's law? Which of the solution shows positive deviation from Raoult's law? This is memory-based experiment. Question. So acetone and ethanol shows positive deviation. All the other mixtures shows negative deviation. Okay, because when you mix acetone and ethanol, because of the hydrogen bonding, volume will increase, and the delta H also becomes positive, endothermic reaction. All the other are exothermic, and delta H is negative. All right, and this is an ideal gas. This is ideal. All right. So the next one is, which of the following solution shows negative deviation? The negative deviation is shown by acetone and chloroform. So this is a solution which shows negative deviation. Acetone and chloroform. This question is also based on your memory. All right. So these two, I gave you the chart and not the chart, the video. You can stop that place and check the examples for ideal and non-ideal solutions. The next question, which of the following is incorrect with respect to an ideal solution? In the first question, we learned delta S, and here they've not given delta S. All these three options are same. All these three are correct for non-ideal solution. This is not correct. This is not equal to. So the answer for this question is this. You should remember this delta G is called as free energy. Free energy is equal to delta H minus T into delta S. So free energy of mixing, when you mix two solutions, what is free energy? Energy associated with a reaction mixture which can be converted into useful work is called as free energy. Energy stored in a system which can be converted into work will be called as free energy. Now delta H is what? Enthalpy of mixing. T is temperature, and delta S is what? Entropy of mixing. So delta G is equal to delta H minus delta T. This is called as Gibbs equation. This is called as Gibbs equation. Okay, to find out whether the component, the reaction is spontaneous or not, we'll use this Gibbs equation. Now, delta G of mixing is equal to delta H of mixing minus T into delta S of mixing. For ideal solution, what? Delta H of mixing is 0. When for ideal solution, delta H of mixing is 0 means what? Delta G of mixing will be equal to 0 plus T into delta S of mixing. Delta H of mixing, or we can write delta G of mixing is not equal to 0 because this value is there. Since delta G is not equal to 0, for ideal solution, delta G will not be equal to 0, as well as delta S of mixing entropy will not be equal to 0. Mathematically, we also proved why delta G is not equal to 0 based on the equation called as Gibbs equation. For this particular question, the answer is option D, fourth option. Wow. Then this is the next important topic that is called as azeotropic mixture. What is this azeotropic mixture? Now I mix ethanol, C2H5OH, ethanol with water and asking you to separate. How do you separate this? How do you separate? How do you separate this? Ethanol and water is mixed. How can you separate this? How can you separate this? If you're not able to answer, it's okay. At least type the answer in the chat box so that I can see. Huh? How can you separate ethanol and water? All the science students from school, you have learned this. Tell me. Have you heard of the term called as fractional distillation?
Yes, sir.
So
Yes,
we
sir.
can separate this based on what? Fractional distillation. The boiling point of ethanol is 78 degrees and boiling point of water is 100 degrees. So when you subject it to fractional distillation, what happens? When you subject it to fractional distillation, ethanol becomes vapors at 78 degrees and that can be collected and condensed. Water remains in the same container. So that's called as what? Fractional distillation. Now the same molecules, I'm taking ethanol and water. So 95.5% ethanol and 4.5% water. Here I didn't tell the percentage, any ratio I told. Here ethanol is 95.5% and water is 4.5%. This is called as a rectified spirit. It is called as what? Rectified spirit. This percentage of alcohol and water is called a rectified spirit. Now I give you this mixture and ask you to separate this mixture. You cannot separate it by fractional distillation. Why you cannot separate it by fractional distillation is at this percentage, both the molecule will start boiling at a constant temperature. In this ratio or in this percentage, both ethanol and water will start boiling at one particular temperature. Since it starts boiling at one particular temperature, these cannot be separated by fractional distillation. These kind of mixtures are called as azeotropic mixture. This azeotropic mixture is also called as constant boiling mixture. This is also called as what mixture? Constant boiling mixture. So distillation and which has a common boiling point or same boiling point will be called as an azeotropic mixture. Likewise, 63% nitric acid and water. Nitric acid, the rest is water. The rest is water. What's the rest? It is the 37% water. This mixture also cannot be separated by fractional distillation because this also forms a constant boiling mixture. So this is also an example for azeotropic mixture. What is azeotropic mixture? Mixtures which has constant boiling point will be called as azeotropic mixture. We will learn many number of examples now. Did you understand what is azeotropic mixture? Did you understand what is azeotropic mixture?
Yes, sir.
Now, azeotropic mixtures are defined as mixtures of liquid which boil at constant temperature, like pure liquid, and possess same composition of components in liquid as well as in vapor state. So they have what same components in liquid state as well as in vapor state. Azeotropes are also called as constant boiling mixture, I told you, because whole of the azeotrope changes into vapor state at constant temperature. That means, what do you mean by whole of the azeotrope changes into vapor state? That is, I told you 95.5% ethanol and 4.5% water. So at one particular temperature, both will become like what? Vapors. So that is why we call this as constant boiling mixture. That is why we call it as what? Azeotropic mixture. And their components cannot be separated by fractional distillation. I clearly told you, we cannot separate this mixture by fractional distillation. Azeotropes are of two types. The first one will be called as minimum boiling azeotropes. What is this minimum boiling azeotropes and maximum boiling azeotrope? You should know. For a solution with positive deviation, there is an intermediate composition for which the vapor pressure of the solution is minimum, and hence the boiling point is minimum. So at this composition, the solution distills at constant temperature without changing its composition. This type of solutions are called as minimum boiling azeotropes. What is this minimum boiling azeotropes? For a solution with positive deviation, there is an intermediate composition of which the vapor pressure of the solution is minimum, and hence the boiling is also minimum. So when the boiling point is minimum, when the boiling point of the azeotropic mixture is minimum, then we call that as minimum boiling point azeotrope or minimum boiling azeotropes. Examples for minimum boiling azeotropes, you can see water, ethanol, water, propanol, chloroform, ethanol, acetone, carbon disulfide. All these are examples for minimum boiling azeotropes. The next example is maximum boiling azeotropes. Now, coming to maximum boiling azeotropes, what do you mean by maximum boiling is for a solution with negative deviation. Negative deviation means volume will decrease. And there's an intermediate composition for which vapor pressure of the solution is minimum, and hence the boiling point is maximum. So, a azeotropic mixture whose boiling point is higher, those are called as maximum boiling point azeotrope mixture. At this composition, the solution distills at constant temperature without changing in composition. This type of solution is called as maximum boiling azeotropes. Water and HCl mixture, water and nitric acid mixture, water and perchloric acid mixture, all these are called as maximum boiling azeotropes. Maximum boiling azeotropes. Students, are you there in the class?
Yes, sir.
Yes, sir.
Yeah, we'll continue. I don't know whether you followed with minimum boiling and maximum boiling. It's raining here. We will start this azeotropic mixture in the next class also for a few minutes, but we'll finish off some of the questions. A system that forms maximum boiling azeotrope. The system which forms maximum, all these are not azeotropic, non-ideal solutions. All this at one set of percentages will show it will form azeotropes. Here the answer for this question is the option A, acetone and chloroform. Due to the strong intermolecular interaction between acetone and chloroform, lesser number of molecules vaporize, resulting in low vapor pressure and high boiling point. You should remember vapor pressure is inversely proportional to boiling point. Lesser the vapor pressure, boiling point is more. Here the interaction is high between the solute and solvent. Interaction is high, meaning it will not easily vaporize. When it will not easily vaporize, the boiling point will be less. Here, the less number of molecules vaporize, resulting in low vapor pressure. Since the low vapor pressure is low, the boiling point will be high. Not the boiling point will be low. Sorry, boiling point will be high. Since they do not vaporize easily, the vapor pressure will be less and the boiling point will be high. This relationship you should remember. Vapor pressure is inversely proportional to boiling point. So therefore, the answer for this question is option 1, acetone and chloroform. Two liquids, nitric acid and water, forms a maximum boiling azeotrope when mixed. I told 63%, it's 68%. 68% and 32% respectively. It means. Now they form maximum boiling azeotrope. when mixed in the ratio 68% and 32%. What does it mean? It means AB interaction, solute-solvent interaction, is stronger than solute-solute interaction and solvent-solvent interaction. This means maximum boiling azeotrope. So solute-solvent interaction will be greater than solute-solute interaction and solvent-solvent interaction. The solution shows negative deviation. When the solution shows negative deviation. Since the solution shows negative deviation, vapor pressure is less. When vapor pressure is less, boiling point will be what? Maximum. Therefore, it says maximum boiling point. So negative deviation solution all will have maximum boiling point. Remember. The next question. Which of the following azeotrope is not correctly matched? This is 68% and 32%, that is true. 43% and HI, water 43%, HI 53%, it is not correctly matched. Water, ethanol, this is also rectified spirit, I told you. And water and chloroform 6.8%, this also is true. So the correctly matched is not this. Water and hydrogen iodide is not correctly matched because this is an exothermic reaction. This shows negative deviation. Therefore, they should show maximum boiling azeotrope. It's an example for maximum boiling azeotrope. But here it's wrongly matched. It says minimum boiling azeotrope. Therefore, this is the wrong option. So the answer for this question is option 3. So we will learn the next set of questions, a next set of topic in the next class. Is there any clarification with ideal solution, non-ideal solution, these graphs, what we have learned, all that? Anybody? Please ask me. See, this is important. These graphs are important. They'll ask you to plot the graph and explain ideal solution, non-ideal solution. Are you there in the class, anybody? All right.
Sir, no doubt, sir.
Ma'am, can I stop the class?
Yes, sir.
Yeah, ma'am.